good afternoon, everyone. Hope you had a good break. We'll be back. We are back with some few questions for the tutorial. I'm going to add to these questions. I have a few of them. We start with what is on what I've presented for the two lectures. And then I'm going to add some from on the board, some more questions as we go along. So let's go ahead and do the first three from lecture 1, and then 5, and then I'll add more as we go along. So if you can read the questions, you guys can start attending them. What is empirical, mechanistic empirical, and purely mechanistic payment design? And we can discuss that as well with the online. So please start with the first one. What is empirical, mechanistic empirical, and purely mechanistic payment design? Please go ahead. While you're putting that together, I'll also add some more questions on the board.
जैसे पहले चल रहा था ना वैसे चला ये कभी आपकी काम करूँ
Anybody want to try the first question? What is empirical, mechanistic empirical, and purely mechanistic payment design? Anyone want to give it a shot online? The person who is attempting it. First one, what is empirical payment design? Anyone? If you go back to the flow chart that was there, the empirical design. Anybody want to give it a shot? Speak up. Anybody here? Anybody online want to try? So empirical payment design is when the design is purely based on existing payment structures and known payment performance, right? So you have Astro payment test sections. So you have set payment structures and their performance is known. And you are interpolating or extrapolating any new design based on this existing data. So you're using statistical correlations and safety factors to kind of do the new design. So once again, empirical is purely based on existing field data, right? You have a set number of structures. You know their material properties, you know their payment sections, you know their traffic conditions, and you know the performance data. And when you have say 100 or so, and if your design is within that subset, you can interpolate and you can get your design. If your new design is outside that subset, then you have to apply a factor of safety, you have to extrapolate, and you can do that design. So that is purely empirical design. Let me go back to the slide that I had done before. Right here. So right here, this was the design that we did, empirical design. You have your input parameters right here. You have your trial section, that's what you're designing. You have your input parameters, environment, subgrade, and traffic. You have your several trial test sections, and you have statistical data. You already have field performance. So you can now select any procedure, material type, and thickness, and if you're within that, you can get your new design. So that's purely empirical design procedure. Next one was, any questions about that? The empirical design. The next one was mechanistic empirical. That is, anybody want to give it a shot based on this flow chart? So the mechanistic empirical is when you have your environment, subgrid, and traffic, right? And you have to pick a trial section. You have to make a payment model where you calculate stresses and strains, and you get your mechanical response stresses and strains. Now, that's your mechanistic part of this analysis. Remember, empirical directly skips that part and goes into field correlation. Here, you have to take your stresses and strains. You have to calculate your stresses and strains, and then the stresses and strains are correlated to field performance. So that's the mechanistic empirical design. So you can do a linear elastic, non-linear elastic, viscoelastic, viscoplastic analysis, and that you can develop your payment model and you get your design. And then you compare with your payment failure criteria. If it passes, you are good to go. You check your cost and construct. If it fails, you have a couple of questions ahead of you. Yes. Questions? And if you fail, you have a couple of options. You have to redesign. If it, or you are kind of suspecting the design procedure, you have to go back to the drawing board and calculate this correlation between stresses and strain and field performance. So that's your mechanistic empirical design. The third part is purely mechanistic, which kind of skips this entire process, and you have no field performance. And I covered that in detail in the lecture. You have the ability to predict all the traffic coming in the next 20 years. You have the ability to capture the rainfall, temperature, all of that information going forward, which is not possible. And then your models and material data is so sophisticated that you can predict what's going to happen 20 years from now, right? And that's not possible. So purely mechanistic is not physically possible because it's not retroactive. You're looking at going forward. Mike, can they hear me?
Yes, sir.
Yeah. There's a message.
They say we can hear you.
You can hear. Okay. Any questions about mechanistic empirical, and empirical method? That was the first question on the tutorial. Okay, next one. Explain the use of Ashton road test in a purely mechanistic design. Anybody want to give it a shot? Ashton road test is the field performance. What is the purpose of field performance in the purely mechanistic design? Anyone want to try? Online or in person? Want to give it a shot? What is the role of field performance in purely mechanistic? Once again, what is purely mechanistic? Where you can use purely input data and predict the performance, right? Like you have this ability to capture everything that's going to happen and then you predict the performance. What is the role of field performance in that? Anybody online?
Analyze the condition of payment.
Only to check the accuracy. So usually the role in the design is nothing, because everything you can predict accurately. So you do not need the accelerated field performance data at all for purely mechanistic design. Only if you want to check it independently. Otherwise, there is no role whatsoever. There is no need for calibration, nothing like that, because you have the ability to predict that. So it was meant for you to think through this a little bit as to whether there is a role of field performance in a purely mechanistic design. And the only role is just to give it an independent check, but otherwise that's not needed. Next one. How can one improve the accuracy of the mechanistic empirical design? How can one improve the accuracy of the mechanistic empirical design? Let's go back to this again. Right here, once again, mechanistic empirical is once again you get the parameters, environment, subgrade, and traffic. You select a trial section, you develop a model, you calculate stresses and strains, and then you correlate them with field performance, right? This is the key to the accuracy of the mechanistic empirical design. So if I do not trust that correlation, I have to get more field data. Okay, so I have, like, as I told you earlier, New Jersey Department of Transportation, we kind of recommend them to do this kind of analysis every so often to increase the accuracy of the stresses and strains and the correlation with field data. And that is how the mechanistic empirical payment designs will get more robust and more accurate. Another way is, of course, spending more time in input parameters. Always, the more investment we do on environment, weather, traffic, the more accurate the model is going to be. That costs money as well. The detailed data collection is costly, and then again, making the model more accurate is also one way. So there are multiple ways you can make your mechanistic empirical design more accurate. Any questions for me before I move ahead? Yeah.
When we say we are correlating the stresses and strains to the field data, but in the field we cannot actually calculate the stresses, right? So how do they correlate stresses in the field?
Yeah. So that's a great question. So one of the ways is that you need to instrument some of them. So that's correct. So you will have to take some sections and actually instrument them to stresses and strains. Another way is actually just measure the surface deformation. So, like for the easiest way is like deformation at the top, that can be measured, but that's not the most thorough way of evaluating. So, if you are not able to instrument them and get the stress and strain, at least go out and measure the surface deflection of the pavement, calculate the cracks. At least you get accurate field data and the surface difference. The problem with not measuring stresses and strains is that you cannot correlate what caused the cracking, right? The cracking is happening from the tensile strains, correct? And if you don't have that, then you cannot close that loop. So rutting is easier, a little bit easier, but cracking is a little more difficult. So yes, you might have to instrument some sections. That's a good question. Any other questions? But we're going to finish this one. What is why is failure criteria needed in the design of payments? And what do those criteria depend on? Anybody want to give me the answers? Even we covered this in detail as well. Anybody online want to try? Anybody here want to give a shot?
Some calculations with the requirements.
Right.
So some criteria is needed so that we can verify the design.
Yeah. So you
And
need
the criteria depend upon several factors. For example, if you talk about the fatigue criteria, it will depend upon the mixed properties, it will depend upon load thickness, traffic loads.
great. So so the failure criteria is needed because there has to be an end goal, right? So if I say I want my payment to last for 10 years, 15 years, 20 years, so the question comes, what does that mean, right? What does last mean, right? Where does this end? So you have to say, oh, rutting has to be less than 1 inch, right? Or rutting, cracking has to be less than 10% of the area, right? So something, there has to be a goal that you want to achieve that after 20 years. So I don't want the payment to run. Now that criteria I want to be emphasized needs to be completely dependent on the safety, not on anything else. So it does not depend on the payment structure, not on the materials, none of that. It will depend purely on the safety of the traveling public. So let me give an example. So for example, if the failure criteria of the design of payments for rutting is 1 inch, right? So you know what to strive for, right? Like after 20 years, I don't want rutting to be more than 1 inch. Now, where did that number come from? That number came from the fact that the water stored under 1 inch of rutting will not cause hydroplane, right? It will be safe for the drivers, right? So it does not store enough water, so it loses contact between the wheel and the pavement. That's number one. Now, if you say 10% cracking or fatigue cracking, 10% of the area, that means that is where you have your ride has become so rough that you're going to have either tires are getting damaged or you're going to have toppling of cars or something unsafe driving condition. So you have 10% cracking, some have 20% cracking. So the criteria depends completely on the safety, not on the pavement or the material itself. Okay, there might be other criteria for the lab, there might be other criteria, but in the design framework, it is completely dependent on the safety of the driving public. I hope that is absolutely clear. I can and did I answer your question? I want to make sure all the online folks understand what the failure criteria is needed to know the end goal. Number one, and second, to that depends completely on the safety. Does that answer? Next one. When do potholes typically occur? And explain your answer. Want to give it a try?
So, I mean, water interfere with the movement and when it is like trucks and all moves into it, then typically at that time potholes.
So when either the subgrade is deflected,
Yeah.
and surface force is rutted.
Right. So pothole, as I told you earlier in my slides, is when you have many things going wrong, right? So pothole is a very severe distress that happens, and that could happen due to all the three primary distresses happening. Number one, rutting, fatigue cracking, or thermal cracking. Primarily, it is the combination of rutting and fatigue cracking, or the alligator cracking. Sometimes, or many times actually, it can happen due to poor construction. We talked about traveling, not paying attention to proper construction techniques. So when potholes happen, you have missed many points along the way that has caused that to occur. So traveling public sees potholes on the roads and they see that is the first point of failure, but that's backwards. It is one of the last things that we want to see, but it's something that the traveling public really sees that front and center. So I hope that answers some of the questions. And I had also brought up a picture, I think, in one of the slides right here. So this one is what I had mentioned here, right? So this is the pothole right there, and then you can see the cracks form, and that's coming from alligator cracking, and that's something to monitor. Okay, please explain two ways of identifying which layer rutting occurs. For example, top layer or bottom layer. Anybody want to try? How when you see rutting on the top, how do you know whether it's the top or the bottom? How do you know? When you see rutting happening on the surface, how do you know that it is on the top or the bottom?
Sir, in bottom layer, the surface will be not deteriorate.
Yeah.
And if it in upper layer, the surface will be deteriorate if it is in the upper layer.
Correct. But my question here is that if I see a depression on the surface, like it's a half inch of rutting, right, 1.5 millimeters, how do you know where it is coming from? Whether it is the top layer or bottom layer? Yeah.
According to foremost, exactly.
Right. It's according to the shape of the rut. Correct. Correct. So if the shape, right.
Yes.
Go ahead.
If there is a human on the asphalt surface, similar to what happens in Tezagi's view failure, is a caving over there. So probably the failure is located within the asphalt mix itself.
Right. So if the rut is very narrow and it just follows the wheel path, so if the rut is very narrow, right? So if it is something like this, right, and that's your wheel path, right? Now you know that rutting. The chances of this happening is very. That means the rutting is right at the top. That was the question, right? That means that the problem is in the top layer because it's very localized. It's right near the wheel path. Now, if I have a wheel like this, right? And I see rutting something like this, right? Now, it is not happening due to the top layer. Something went wrong in the bottom, right? That is one of the ways to find it. What is the most exact way to find it? If I'm willing to spend the money, so this is one way, indirect way, right? Okay, it's very narrow, but as I told you earlier, it's not going to be an exact science. Why? Why is it not going to be an exact science? Why am I not going to see this and this very clearly? Any guesses? Why will I not? Why is it not very obvious? Because
we do not see at very less stretch. We see at a large stretch.
right, and also the tires, the vehicles are not driving in one straight line, right? They are wandering, right? So it's not like it will change once you have automated vehicles. So the vehicles are not going in one straight line, right? So your vehicle itself has almost 6 to 12 inches of wander when they're traveling on the trail. So having said that, you are not going to see a very tight rut depth along the wheel path, right? You are going to see a little widening either way. Having said that, to see the difference between this and this, I made it seem very obvious, but it may not be that obvious. You know, it's a much harder problem than that. But if I'm willing to invest the funds, what is the most exact way of determining where it happened?
Ground penetrating radar.
Ground penetrating will give you voids, close. So that will give you voids change, that's correct, right?
The deflection test, simple deflection test.
Yeah, diffraction test also will be very hard, but you have to do something very much more severe. Yeah, you have to cut the whole section of the roadway. So you have to actually slice the entire roadway, and if you slice the entire roadway, you will see something like this, and then if you see something like this, now you know, right? That's the most thorough way, which no DOT or PWD will like to do that. Nobody likes to make holes in the roadway, right? So that's the most exact way of you have to make a cut in the entire roadway kind of see what's going on. Let's do the next question. Do you have any questions online about this? Explain the mechanism of failure of pumping. Anybody want to try? Explain the. Anybody want to try the failure? Which payment type is this?
Rigid.
Rigid payment, right? Concrete. Yeah.
Yes.
Yes.
Like 4 years of better.
Can you repeat? How does it happen? How does pumping happen?
More brightness of layer.
Yeah. So you have something else. Something else. Anybody else?
They force the water and soil splitting.
Yeah.
So I
So
wanted to
right. So you go ahead.
From the lines, water will penetrate into the slab, then with the mud, the water will become up the top.
Correct. Correct. So you have failure of the joint. The joint loses the structural integrity, and then you have this happening. So right here, right here. So right here, you have the pumping happening right here, and here you have a slab here, right? And now you have lost the structural integrity between the two cases. If this is done perfectly well, this would act like a center of the slab, right? Both of them would have complete continuity. The fact that they lost the continuity when the vehicle comes in here, it deforms down, right? And then when the wheel comes just on the other side, the trailing slab rebounds, right? And the leading slab deforms, right? Of course, it's exaggerated. And then over time, the seal completely breaks, water enters, and then you have the fines that are the subgrade loosens up because water entering, then it pumps out the sand, and you see this happening right there. You see the soil, sand right there. That is the sand coming from the bottom, and that's really bad news because you have lost support of the failure. So that's. Any questions about this one? Where do you find alligator cracking? New flexible element, old flexible. So these are very straightforward questions. So around quarters of all concrete payments, so they are very straightforward questions right there. But alligator cracking, where do you find it? Old payments, right? It's a bottom-up crack, right? You should. It's not happening at the surface, and it takes a while. Why it's old? Because by the time the crack comes on the surface, it may be 8, 10 years old, right? So you have a long time, and again, that's a bottom-up crack. And around potholes in flexible payments, right? Not in poured concrete. It's not common. All right, I want you to try this one here. What are the critical mechanical properties that impact rutting, fatigue cracking, and thermal cracking? I want you to try that. What are the critical mechanical properties and responses? Let's try that as well.
Elasticity of between them.
Huh?
Elasticity of between. Elasticity of.
Yeah, elasticity, correct. So elastic properties slash, let's look at one more thing, that mechanical properties. Slash parameters that impact rutting, fatigue, and they're all different. Let's start with rutting. We explained the phenomena of rutting. Can you go back to your notes there? What mechanical properties or parameters that impact rutting? Anybody want to try?
Vertical subgrade stresses.
Mechanical problem.
What did you say?
Subgrade stresses. Vertical subgrade stresses.
Subgrade stiffness. Okay. What else? That's good. Next one. What else? So this will happen when you have a very low subgrade stiffness, but there is a catch here, right? You can subgrade stiffness can be low, but you can really make a very thick pavement and protect the subgrade. Remember, the whole purpose of the pavement is to protect the natural soil. So subgrade stiffness is fine.
Yes.
Low subgrade. What else?
Modulus of alpha. Modulus of asphalt means fine.
Modulus of
Modulus. Okay. The modulus. That's good. So modulus of asphalt. Okay. So modulus of asphalt is low. Okay. So that could happen, right? So you have low E value of asphalt at that temperature. It's a what temperature does this happen? What temperature does running happen? Higher, 30, 40, 50 Celsius, right? Or greater, right? Modulus of asphalt. What kind of failure is this? Rutting is what kind of failure? Usually. What mode of failure is rutting?
performance,
Structural failure.
structural failure.
What mode? No, I mean to say, well, it can be a material failure, it can be a structural failure if you see a subgrade stiffness fall. But that's right. It's a subgrade. If you have all the pavements rut, then you have a structural failure. You have not provided thick enough to protect the subgrade. What else? How else can it fail when it's at the top? When the rutting happens at the top.
That means unstability mixture.
Yeah. So you have
Yes.
Unstable mixture. You have shear failure, right? You have unstable mixture, right? And you have shear failure. Okay. That's when you have. How can I prevent that? We'll come to that. Let's look at this. Modulus of asphalt with those subgrade stiffness. Somebody mentioned about structural failure. How can I prevent rutting to not happen at the subgrade? How can I prevent that?
Introduce the layers.
Increase the layers. You're absolutely right.
Yes.
Increase the layers. Increase the layers thicknesses. Right. That means
Stabilize the material of the grade.
yeah. So you increase the subgrade stiffness by stabilizing it. But the reason why you don't want to talk about stabilizing the subgrade, but at least add the reason why I say that, because at some point you're going to hit the natural soil, right? You're always protecting the natural soil. So if you talk about stabilizing the subgrade, that means you're taking the natural soil and it almost becomes like a sub-base layer, right? You're but there's another layer below that. That's a natural soil, right? So you're in effect protecting something else. So you want to stay away from any discussion about tampering with the natural soil, because that's assume that is there, right? So you want to increase the stiffness of the layers above the subgrade. Right? So that can be stabilized. So that can be stabilized, that can be a stronger layer, so on and so forth. And again, you are trying to make the load far away from them. Okay, what else? Anything else that I missed that you want to think of? What causes rutting? This is very good.
Can use geogrid and geogrid.
Geogrid, yes, you can use geogrid because that's right. So you can use geogrid right here to kind of stabilize the layers above that. Okay, what else? That's good. Anything else on rutting? Modulus of asphalt, unstable makes a shear failure. You make your aggregate stronger, right? I talked about binder, so on and so forth. What else? Anything else comes in mind with rutting?
Yes, for asphalt layer, you can use polymers also as a solution.
So polymer modified asphalt. Okay. And you make the, you are increasing what? The shear stiffness. Remember the aggregates moving with respect to each other. So you increase the shear stiffness of the aggregate. Yeah. The thing is the speed of the cars, you don't want to touch anything that's outside the pavement. Because remember the traffic is what you're designing for. Right? That's not in your control, but you need to know what it is. So the weight of, if you're stopping the vehicles from coming, then that's not the pavement. What else?
As per se, increase the speed of as you say, increase the speed of traffic.
Increase the speed of traffic. As I said, you don't want to mess with traffic at all because anything you do on the, so see, if I go back to that flow chart, something that's not in your control is environmental factors, traffic, and the natural soil. Right? These are given to you. These are the parameters that you have to address in your pavement design. Right? So if you try to stop traffic, reduce traffic, then the whole problem is mute, right? Oh, I will tell trucks to not come on this roadway. I have solved the pavement problem. Does that make sense to you? So you want to stay away from anything that will make the traveling public change their behavior, right? Know what I mean? That you have to remember that. You're there to serve the traveling public. They are going to travel the way it's going to travel, and then you want to adjust accordingly. Does that make sense, everybody? Anything else? Can I move on to the next distress? Okay, let's try fatigue. This was great discussion. How you're capturing this. Next one, let's try fatigue cracking. When does this happen? Which low? What range? Yeah, so not very cold, not very hot as well, right? So around, let's say 5 to 25 Celsius, give or take, right? Approximate. So it is not flowing, it is not very hot. Around this time is fair enough, right? It doesn't get too hot, So fatigue cracking happens there. How does it happen? First, try to understand how it happens and how can I, what?
Repetition of load. Repeated load.
Repeated loading, correct? So it's due to repeated loading, correct? So you have repeated loading, it happens during fast moving traffic, right? So somebody mentioned increase the speed of traffic, right? Now this happens during heavy fast moving traffic. So if I increase the traffic, I will create this problem, right? There's always a risk in doing such a thing, right? So if I increase the traffic, this happens mostly on highways, fast moving traffic, right? So basically, as I mentioned, every time a traffic goes on, deforms, it comes back. It deforms, it comes back, right? And there's fatigue happening, right? So if the pavement is not able to handle these changes in this, you're going to have a crack form right here, right?
If you use bitumen,
Yeah.
bitumen, like unsuitable bitumen for X location.
Yeah.
For example, if you should use bitumen in a cold region and you use stiff bitumen in that region, you will get fatigue crack.
Right. So if you want the material, so the point is like, do I want to capture the light? So the example I give is that you want the material to be flexible, right? It's going to repeated loading. So you are hammering this again and again, right? And you want that material to handle that deformation without cracking, right? And a flexible material like a rubber, right, that can go back and forth, like a rubber band can handle this. So you want the E value, the flexibility, you want the E to be low, you want it to be flexible. Does that make sense? It's exactly reverse than rutting. In rutting, you want to be E has to be as high as possible. We wrote that down on the board, right? So I change my temperature regime it has become the requirement is completely flipped, right? So that's why you want the E to be as low as possible, as flexible as possible. What else? How else can I prevent this? Prevent this.
I can add something.
Yeah.
Professor. In mechanistic empirical pavement design guide, divided static cracking into two types, bottom up and top down. For bottom up, this become from base layer. If the weak weak base layer, you can get bottom up fatigue crack in your pavement.
Correct. So you can, so you have a certain tensile strain developed, right? Or a stress, right? And if this exceeds a certain brittleness or ductility, it's going to create a first crack. Everybody understand that, right? So there's a load. So how can I minimize that, right? So that's the problem. The load is on the top, correct? That's not in my control, right? The amount is not in my control, but I know what it is. So if I can move this point away from the top, I can drop the tensile strain. Simple beam theory. Right? That's number one. I made this thicker. Second one, the participant said, you can make the support very strong. Right? This is not in air like a beam, right? It is in contact. So you can make this E1, you make the E2 very strong. And this or this strong. This thick, sorry, right? So you have a couple of options, right? I can make this very thick, this drops because I'm moving it away from the load, right? Or make this very strong, right? And this will also drop, right? Because I've got enough support. It's not in air. That's the thing about pumping, right? In pumping, remember the water takes the soil away, right? And now this is almost in air. It's going to accelerate failure and cause crack. Does that make sense? Everybody with me so far? I'm going to cover this sometime a little bit tomorrow, but I want to completely understand this. In fatigue cracking, this is a critical mechanical response. Everybody understand that? Right? You have to understand that this is, if I can minimize this, I will minimize fatigue cracking. Everybody with me so far? Now, look at it a couple of ways. What are the parameters that is very close to this in my control as a payments person? Can you tell me what are the parameters that are in my control to minimize this? Can anybody online or here tell me?
So minimize the deflection.
Tensile strain.
Right.
Yeah, just remember look at cracking, tensile strain. What are the things in my control that I can do to minimize this? Remember, environment, traffic, and natural soil is not in my control. Can anybody tell me what are the things in my control?
So material quality.
Okay, so
Quality of material is in my
just
control.
look at this. Just give me this figure right here. Which are the things in my control in this figure alone that I can minimize my epsilon t?
Dimensions.
Thickness.
Thickness. Okay, so I think this is in my control, correct? One, I can make it thinner or thicker. That will impact this. What is something else?
Type of binders.
Just in these three. Just in these 3, 4, 5. This is the natural soil. Let's say this is the natural soil. I'm not touching it. Right? What else?
The modulus of elasticity.
Which one? So binder is just a constituent of asphalt. Which one? We just discussed this one. I want to minimize my tensile strain. Right? Right? What are the things in my control, looking only in this figure, that will minimize my tensile strain to minimize my fatigue cracking? Just looking at this figure, if I increase my or decrease my E1, right? That's one, right? Will impact my tensile strain, right? That's what. If I increase my E1, what is happening to my cone of distribution?
So you will increase E1.
If I increase my E1, what happens to my cone of distribution?
Cone will widen.
Will widen, correct? I will, so remember I give you the example of speed. My cone widens as I increase my E1, correct? That means that thing becomes more efficient, right? Remember, I gave you the example of steel. If I put a steel slab, the cone of distribution is going to be completely flat, right? Very efficient, but very expensive. Okay? I want you to pay attention here. If I make this very hard, right, the cone of distribution is going to be very wide. What are the stresses going to be here?
Negligible.
Very low. You are absolutely correct. Correct? Is everybody with me so far? But, now this one, I just said make it flexible. Right? Am I contradicting myself? Right? Just now I said if I increase this, correct? If I increase this, I make my cone of distribution very wide, I can make my epsilon t very small. Fair enough. Right? But just in my previous discussion, I said make this as flexible as possible. How can that be possible? What is the contradiction? Anybody online? Yes, go ahead.
If there is increase in stiffness.
Yes, of course. Of course. So I will drop the tensile strain. But just in my previous discussion, I said you want to be as flexible as possible, keep bumping down and on. Then why am I talking opposite things? What is missing here? This is why fatigue cracking is the most complex distress to manage. Anybody online want to think about it? Let's look at this. There are a couple of things. If I can, okay, increase my E1. Remember, I'm only working in this temperature range, correct? That's all I'm working on, correct? I cannot increase E1 that much to drop epsilon T too low. My material cannot do it. I will repeat what I just said, right? I don't have this magical material that between 5 and 25 C, it will just become so high that it acts like steel. Not possible. I cannot do it. My asphalt cannot handle it. Does that make sense? Everybody with me so far? Therefore, I am stuck with how much I can increase my E value. I have only so much to work with. I am going to get certain amount of tensile strain that I have to live with. I can't magically bump it up within the cost of the layer. Does that make sense? Having said that, I am going to incur some tensile strain. And because I am going to incur some tensile, I want the material to be flexible. Is that very clear to you? If I could magically make it very, very stiff, and I give this example, it's like me banging this on the desk. I can do million repetitions of this marker on this table. Nothing is going to happen to this table, right? Because I made this table infinitely stronger than the marker. I cannot do this for the pavements. Not possible with the current economy, right? So I have limits to this. Theoretically possible, but I cannot do it. That means I have to make it flexible that it will then, it has to come back. Fair enough, everybody with me so far. And then the second one is, last one is E2. Everybody with me. So H1, E1 and E2. Got it? Yes? What is this? This is a very simple response. Having said this, if I were to identify isolated H, E1, E2 and epsilon T, looking at the location, what can you see the location of H, E1, E2 with respect to epsilon T? Location of these parameters. Very simple answer, actually. Anybody online? Anybody? It is very closest to epsilon T. I'm not looking at this layer. I'm not looking at a couple of layers. So any parameter that touches this will have the greatest impact on this. Common sense seems common sense, right? But you guys did not respond, right? So, right, H1, E1, E2 is closest. Now, second question. If I were to pick which one will have the most impact of epsilon T, what is your logical answer? Which one would you pick if you had the choice? Looking at this, which one, where it would have the most impact?
Width of the section. Width of the section.
Why? You're right on. Why? Why?
So,
Anybody online?
it is the difference between the load point of the load and the
Excellent. Anything between this parameter and the load, anything between the two will have the most impact. Anything below that will have minimal impact, right? The problem is the load, right? So anything between these 2 points, if I change, will have the most impact in dropping this, right? So if I guess E2 is correct, it will have an impact, but I have to change E2 a lot to make the same impact as increasing a little bit of H, right? Because E2 is up below the layer. Does that make sense? If my epsilon T was here, then fine. But my epsilon T is here. Does that make sense to you? This is the concepts of optimization of the payment design. You need to immediately understand, oh, this is the parameter I want to control, number one. And second, what is that and the pay and the load? Between these two, if I can select, I have only finite number of dollars or rupees, right? Does that make sense? But then if increasing the thickness is the easiest way and cheapest way, I will do that first. But me getting material from far away is more expensive, then I can't do it. That's number one. Second, if increasing the loadway, I'll hit the bridge. That means I can't increase the loadway. Okay, I'm constrained by H1. Then I have to change this. Does that make sense to you? This simple exercise will make you optimize your resources very quickly. Does that make sense to you? Just by simple looking at a tensile strain and the related to the load, I can optimize what it will take. Does that make sense? Everybody with me so far? And fatigue cracking is one of the most complex one. Rutting is the easiest because it's right at the top, right? And fatigue cracking is not important. Questions for me? Any questions online?
But is there any correlation between the modulus of elasticity and the cost associated?
Oh, 100%. Yes, because you have to make it angular. Like you're going to ask on site, right? Angular, polymer modified bitumen, compaction. Like it's all about cost, right? So you can. Somebody mentioned about polymer modified binder. That's expensive, right? Those cost money, right? So the moment, anytime you increase your E value, there is a cost. Anytime you increase your H value, there is a cost, right? And so let me give you an example. Right here, I have a load P. I'm just going to take a 2-layer system, right? My top layer is I'm just going to work in US units for now, 2 inches, right? That's it. Protecting the natural soil. Simple, right? I'm in this situation, right? H1, H2, E1. Okay? Everybody with me so far? Tensile strain here. Tensile strain here. Correct? My goal is to prevent fatigue cracking. I'm coming back to the same concept. That means I want to minimize this. Correct? Now just think about this a bit. Logically, a load is a thing, right? Now, if I change, we're talking about the quality of E1, right? Think about it this way. If I went from E1 to 2E1 here, and I went from E1 to 2E1 here, I want everybody online and just to think with me. Which one will have the most impact? Online and just think and tell me. You understood the question? Everybody with me?
So impact in what sense? Like
An epsilon T. Right? Like in terms of the increase.
in epsilon.
Second one, sir.
Second one will have the most impact. Why?
Because there's due to higher depth or thickness, there will be less dependency on E1. Yes, first one.
100%. You're correct. Right? So here, this going from E1 to 2E1 will have minimal impact on epsilon T. But here I'm so close to the load, any changes, any investment I make on E1, because I'm answering your question, does it cost? Yes, it does cost, but if I am stuck with 2 inches for whatever reason, it's worth every penny to me to increase V1. I'll make a tremendous impact in epsilon T. Does that make sense? But here I'm so far away. This for the epsilon T, my load is so far off that whatever I put here is not going to make an impact. I've put this problem so far down. Does that make sense? More than 2 feet away, right? For 4 feet, right? Does that make sense? So this is very critical in your response. Does that make sense to you? I already put 50 inches, right? Now I could put dirt of 50 inches and I'll be okay, right? But here I cannot. That dirt matters. That is to answer your question. That is it worth increasing it? This is also going to come in the next class tomorrow. That's why I want to. Does that make sense?
Yes.
Anything online? Okay, next one. Thermal cracking.
Excuse me, bro.
Yes. Question. Anybody?
Ratio,
Yeah.
voice ratio play critical role here or no?
What is the question?
The Poisson ratio.
Poisson ratio?
Play here or not?
Did he ask about Poisson's ratio? Did you ask about Poisson's ratio?
What?
What was the question? What was your question? Did you ask about Poisson's ratio?
I say you the Poisson ratio play critical role in this failure or not?
No, Poisson's ratio does not play a critical load. If you are looking at what epsilon r is about epsilon z minus 2, or what is it, minus u epsilon x, right? Something like that, right? So this is so small. The range is between 0.35 to 0.5. You're looking at such a small number that it makes very minimal, right? So you are looking at a very small range of number to work with. And actually it doesn't even such a small, it's usually 0.3 and 0.35 and 0.45 or something like that. So yeah, so it doesn't have a lot of Poisson's ratio.
Okay. Okay.
Okay, next we get thermal cracking. How does it happen? When does it happen?
Geographic location of the basement.
Okay. When does it happen? So primarily very cold areas, correct? Very cold, right?
Yes.
Yeah. Then when does it happen?
Perpendicular.
When you have a cold front coming in. Only when you have a cold front coming in, you will see it. When you have temperatures go from 10 Celsius to minus 40 Celsius, not freeze thaw. This is not a water problem. It's a thermal contraction expansion problem, not the water problem. So it happens it doesn't happen even in my state, in New Jersey. It happens in Canada, in very cold regions where you have a cold front coming in, and in a very short period of time, it becomes very cold. And what are the parameters that impact it?
Bitumen.
Viscosity, stiffness of the bitumen, right? So, okay, so E of the asphalt. So we are looking at the pavement system. So let's look at the E of the asphalt concrete. What is it, a load bearing or non-load bearing distress? Is it a load bearing or non-load bearing? Non-load bearing. It happens perpendicular to the traffic, correct? What else? E of the asphalt concrete. You want it to be high or low? Want it to be high or low?
Low.
Low. You want to be very flexible. You saw the requirements are changing every time. What else? What else? We discussed this a little bit while ago. Online.
What we mentioned?
What are the other parameters? What are the other parameters that will impact that? thermal cracking. So you have asphalt concrete due to the forefront, right? When you have a forefront, you have thermal contraction is alpha delta T. Delta T is the contraction, correct? So alpha is the coefficient of thermal contraction. What else? Stress is equal to E times epsilon. So you have your epsilon here, you want your E here, you want both to be as low as possible. Right? When does the crack happen? When does the crack happen?
I think
Yeah. Go ahead.
if the water infiltration, the underlying layers.
Right. So this, the water infiltration thing is by this thermal is purely related to water. So you have this happening. Your time strain, and when you have temperature drop, stress, you have something like this. Stress is temperature drop. It meets the. You have could be equal cracking, right? So you just be as flat as. Remember we discussed this. You want to be as flat as possible. That. Anything else? I think that's. I can add more questions, but that's all I had. I'm going to add more questions or your thoughts. You good?